then why it becomes, okay, so let me first say that if there is nothing else, if this is a sharp notch, then just dl, so 4 into dl into 4 surfaces created of with w, so this is the surface area required, surface energy density is say this. So equal to will give me sigma c that is required for nucleation, and that would be something like, apart from some numerical factors which of course depends on the approximation of this kind of geometry of the stress release regions. I mean, it's not entirely circular, but I have assumed a circular one just for simplicity. You do better things, then you will get something, some numbers here which is different from 2 pi by 2 and something. You will get something, some other number, but most importantly in terms of the modulus of elasticity and length, you will not get anything different. You will get it, I mean, stress proportional to strain, I mean rather strain proportional to stress, the Hooke's region or linear region, if it is valid up to the breaking point, that means in a brittle solid, you will always get this kind of structure, that sigma square will be proportional to this, and one length will come out, because if it is, typically energy density is and the density volume is L to the D, and this will be L to the D minus 1, so that would be always L left, and surface energy density and linear elasticity modulus will be there, and this would be the form. The prefactor may depend on the geometry that you assume or you find appropriate. So in terms of scaling of this will remain like this. Then there was a part of discussion which I wanted to draw, is that, I mean, if you have some random defects which are not necessarily which are not percolating, but let us assume that they are and this is the sample, and it is under stress sigma. Then the scenario changes. Here you have a particular nucleation stress for the crack to propagate, and that will determine the strength of the whole system. Here you may not get that, and in fact I think phenomenologically people have studied many years, I mean the failure probability in this kind of case. Okay, by the way, we still assume that the stress release regions are still not overlapping, so in a sense they are independent. So but if you do that, what you will get is okay, let me gamma 4, what was there, dl into the weight w. So this is this calculation, and this is failure probability under stress sigma. We have to do it like this, and sigma is this, sigma 0 here, and failure probability 1 is here, and you will typically get a thing like this, curve like this. For volume bigger one you will get like this, so V1, V2 is greater than this, and so on. Here you cannot talk of a particular failure stress, they would asymptotically touch, but if you say that the failure probability 90%, then you have a sigma c, but that sigma c is a volume dependent one, in the sense that volume decreases, the sigma c decreases. We kind of explained that, and that we wanted to do in a better way, but our argument was that essentially the Lipschitz kind of argument, statistics, is that, I mean, if you have a defect, it is easy in a one-dimensional chain, but you can do it. I mean, you have L sides, and as I said, I mean, this was the first kind of appreciated and precisely documented by Leonardo da Vinci, and it still remains a major problem in this kind of extreme statistics. I mean, this makes the fracture statistics different from, say, elastic response or linear response of disordered solids, or conductivity of classical disorder solids. For classical conductivity problem, classical disorder things, I mean the percolation theory is enough, and that is self-averaging. You have a particular failure, a particular elastic constant. I mean the thing is, this elastic constant remains even if you have this kind of defect. The elastic constant will have a thermodynamic value that is valid and defined in the V going to infinity limit. Surface energy density will, of course, that doesn't depend on these things. These linear responses do not change, do not become completely different. They depend on the disorder content, but they do not become dependent on the volume, so that in the volume going to infinity limit they disappear. But what we wanted to tell is that if you have disordered system and there is no one is dominant enough, then there is no clear L that has to be used. If you do the calculation properly, you will find that instead of L, some volume dependent term will come, a log volume will come. And so in the limit volume going to infinity, the system fails at any point. I mean, so that means this is not a defined quantity, because it has a statistics which is not self-averaging, and that is what our intention was. And a simple argument was that if you have P probability of defect, then to get two successive defects is P square, 1 minus P on both sides. To get three successive defects is P cube, and then 1 minus P square on both sides. So anywhere you want to do. But if you want to get L length successive defects, then it will be P to the L, and then on both sides there should be the original bonds. So the defect of size L, probability is this multiplied by the volume, length or volume, that goes to 1, means you have a defect of size L. And then that means if you take log L log P plus some 2 log of 1 minus P plus log V will go to 0, and that means L will go as log, this is V, or I mean V or L, whatever you call it, log V divided by log of minus of this log of P. But since log P is less than 1, so log P is negative, so you just have this. So if you, this actually for disordered case and no one dominant, you will get sigma C going as 1 upon, okay, something like gamma Y, but that is dependent on P, and it is defined. It's a thermodynamically defined quantity. Even in the volume going to infinity limit, it is a defined quantity. It is dependent on P minus Pc, the percolation threshold, but it's a defined quantity. But here you will get log V. And that means you do not have in the V going to infinity limit anything. I mean any force will break the sample. I mean that is how they. I mean Galileo also justified why we cannot build big buildings. Animals cannot. Well, with this kind of bone structure or bone material. I mean carbon materials, calcium materials. It has a finite strength, so very big animals would anyway fall and break their. I mean, they would not be stable in structure. So that's why we do not get arbitrarily big size of things. With log volume, inverse log volume to the power half, our structures fail. If you so to do that, we wanted to do some calculation, but before that, we wanted another thing. Let us come to percolation problem here, because percolation is a mathematical geometric model. It is easy to define on lattices and make it precise. So that's why usually people take some lattice. Essential problem, and you say that okay, there is some Imagine, I mean, it's continued for, and you think that this side has a connection to some and this is non-conducting, although I have put some potential difference across, there is no current, and then I put some bonds randomly. Okay. Then I am putting randomly as far as you can imagine what I am doing. Now you can see, and okay, let us try to think of the current from as measured here and as a function of p going to 1 is here, it is here. So this point at p equal to 1, of course all the bonds are like these thick bonds, they are conducting, so the current will flow. And you can see that the flow will be through these parallel links, which is important, and I will come to later to utilize that. And but that's trivial, I mean, so that's the maximum current that can be flowing through this network. But and of course it is current is 0 when there is no bond. Now the question is 1 or 2 bonds will not make, I mean, so you think that, I mean, some finite p you don't see, but you can think of some fluctuations. Say for example this, for some fluctuation, this is there and this is there. Four bonds, but they are all on a line. Of course there will be a connection, but that's highly improbable. I mean, it goes down with the size of the sample, because p is less than 1, the probability to have this fluctuation that nowhere else, these all 4 comes here, or all L bonds, this is a L length one, all L bonds fall on this is highly improbable. So on an average, you don't get any current. You get current macroscopic limit at a finite threshold called the percolation threshold, and in many other places you will require this, okay, and then it starts growing. As I said, a growth around this point is important. Now there are various quantities that would be important. One important quantity that will, okay, one possibility is this simple question called the order parameter. Like in magnetic case we considered magnetization as the order parameter. In this case we said velocity of the crack, I mean nucleated crack as the order parameter. That was a thing, but here one order parameter may be very simply defined, is that I take any this I did in a bond way, one could do it on a site way. The sites were randomly occupied with probability p or not p. Oh, by the way, this point is not universal in the sense it depends on whether it is a square lattice or a triangular lattice, whether you are throwing bonds or sites. For example, on a square lattice bond, PC is half. This is bond randomly thrown. Correct, no? Okay. And for triangular lattice site, PC is half. PC site is half. There are some kind of mapping from one to another, but in general bond thing on another triangular lattice would be different, on hexagonal, I mean on other lattices would be different. I mean if you take 3 dimensions and so on. So not only with dimension it will change, it will also change with whether you are considering square lattice or triangular lattice and so on. But the growth near this, the current growth near this will be independent of whether you are taking site disorder or bond disorder. As I said, that kind of similarities are very important, and that's a much deeper thing of in this kind of lattice statistics. as I was saying, that the magnetization growth near the transition Curie point is a kind of deeper thing of the statistics, and you have to think of some other I mean the real aspect of the infinite system and how to kind of accommodate all the fluctuations and so on. And here the fluctuations are also very important. But anyway, so one important quantity that percolation people want to find out, there are generators of the statistics, but I cannot go into all the details. One is, if you take an arbitrary bond, here it is a bond percolation problem, I just take arbitrarily just a point, a bond, and ask what is the probability that it has landed. Okay, so after some time what will happen? After some time maybe this bond will be occupied, this bond will be occupied, this bond will be occupied, maybe this one will be also occupied, and this one will be there, and then this will be there, and then after some time maybe this, okay, maybe this will be there. Oh, not yet. So maybe there this will be there. So then from this end to this end through this end, it has actually percolated. That's the point when just that happens, marginal connectivity, that's the percolation point. And you can ask, if you are above PC, what is the probability, that's the order parameter, that what is the probability that any arbitrary bond that I choose and I try to choose, and then I try to find out whether I am on the infinite cluster or not, I mean the connected cluster or not. So that would be the order parameter, so that I would not use here. But another important point which actually is can give a much more important picture is that I take two arbitrary bonds, choose at a distance r, and I ask what is the probability that these two bonds at a distance r are actually connected, I mean in between they are actually connected through the clusters, I mean occupied bonds. Okay, this is the correlation. I mean I try to find out any arbitrary bond I choose and another arbitrary bond at r distance, and then on an average they are connected. You can easily see that as distance increases it will go down. It of course goes down typically as, and then there is a prefactor which I write as this, because this is a length, this is a probability, so I make it scale free, so length by another length called the percolation correlation length. If we would have time, I would find out what is this. It says you can, okay, we can argue why this. Sometimes this happens is that it is P minus Pc to the power minus new percolation. It's called the correlation length exponent. It actually diverges as you approach the percolation threshold, and so this is the kind of, this is established in various ways, and you can find out, and as I said, this is the correlation length exponent, which is quite an interesting important one, and similar things you can do for the magnets. There are two Weber magnets at a distance r. I mean, what is the possibility that if this is up, that magnet, Weber magnet, the small tiny magnet, is also up at a distance r. Now this r has to be, I mean, averaged over all orientations and so on, and all realizations of the thermal dynamics, and then that also goes down exponentially. Practically there are other correction terms, but essentially this, and that goes as, in that case the correlation, I mean in the called spin-spin correlation length in that magnetic case, or this spin is the Weber magnets. So that also goes down with r, with that length which is called, that's a thermal correlation length, and that goes as T minus Tc to the power new thermal. I mean, so that you can also study. But here we will need this thing, and at the percolation point, this is when you are not at the percolation point, and at the percolation point it goes as r to the power some minus, at this is P not equal to Pc, and where xi is this. And at the percolation point, it cannot be dependent on P, because you are at the what is called self-similar point. We have to utilize that also. It is called zeta or whatever. And that also is an universal number, that is at P equal to Pc. We need these two things to remember. If there is time, we will try to find out nu P and nu P essentially. But that would be, before that, let me finish the major thing that I wanted to finish, at least in this lecture. Okay, so this is this. And yeah, okay. So now let us come. So this is about percolation that at the moment I need. Another thing is, okay, and that would be also necessary, some fractals. Now this correlation length is indicating that correlation length going to infinity means any r is more or less looking the same. I mean, because your r is not important, r by xi is important, and if xi goes to infinity, all distance more or less looks the same. So let me give you a picture, this kind of okay, even if you have an infinite ordered lattice, you have self-similar, because anywhere you stand, if it is infinity on both sides, you do not see where you are. You cannot distinguish. But you do a better job if you can take, okay. So this kind of things were there earlier, say some kind of constructions like, okay, so something like this. And okay, I hope you can understand what I am doing. You can follow the algorithm. I mean, I am always keeping the left top corner at any level free, and otherwise it is self-similar. That so essentially, I mean, from the back, probably you will think that it is a square broken up into 4 quadrants. The top left one is free, but otherwise there is material on the other quadrants. Then you come closer, you will see that, okay, even this one has the same structure. Top left quadrant is free, but other 3 quadrants have materials. And the same. Then if you come closer and so on, at every length scale it would look similar. Now this is of course an ordered one, but you can shuffle it, reshuffle it and so on. The idea is at the percolation point, at this point, this cluster structure is a kind of scrambled form of this, maintaining some of the things, like for example the dimension here. One is mass dimension. Suppose sorry. Suppose I increase the length by 2, factor 2. Okay? Okay. Suppose I am asked that I have to paint this board, this part. Okay? Suppose this is a square. This is length 1 meter by 1 meter. And my contractor or I am supposed to give the cost of the material that would be required. Suppose that is 100 rupees. And if the length and breadth increase by 2 meter to 2 meter, how much you would expect the cost of painting would be? 2 times or more. 1 meter by 1 meter takes me 100 rupees. 2 meter by 2 meter. Board is now 2 meter by 2 meter. How much would be the cost? 4. Because the dimension is 2, and then if it would be a cube that I have to fill up with, say, sand, say 1 meter by 1 meter by 1 meter was 100 rupees, and now it is 2 meter by 2 meter by 2 meter. How much would that cost? 8 times. Because it is a 3-dimensional system, it is you are talking of surface as a 2-dimensional system. Now I ask you that to find that this chalk I used in painting this, I have now increased the length and breadth by 2, twice. Would it be 4 times or not? I have changed the length by 2, multiple of 2. I have length from 1 meter, I have gone to 2 meters. Similarly, this one is also now, instead of 1 meter, it has gone to 2 meters. Now, in painting this, I used a very costly dye. So that required, I will use the same algorithm to paint the whole thing. And then tell me how much would be the cost, how many times it would be. Anyone? Huh? Can you be louder?
Less than 4.
No, less than 4, okay. He is saying it is less than 4. It cannot be more than 4, that is clear. And not even 4. But you do not have any idea how much it will be. Anybody? Any student? Huh? 3 times. Great. This is very simple. Because whatever you do, suppose I spend 100 rupees here, I have to do that thing here and that thing here, because this will be free. So I change the length by factor 2, to the power d is now 3. That d is no longer 2 here. It is less than 2, it is log 3 by log 2. This is the Hausdorff dimension. So this is a fractal dimension. So dimension d is now log 3 by log 2. It is neither 1 nor 2. Previously it was 4 by 4 or 8, I mean, as you said, it was it was 4, so it is 2 to the power 2. But if it is the volume I am filling up, it is 8 times, so 2 to the power 3. That is the way we get the Euclidean system. Now here, the same thing will not lead to this thing. So there is a kind of dimension involved, and that dimension, fractal one, and let me stop there until further is needed. Now let us come to this. Oh, so it is drawn here. So this I have to find, so I want to find failure probability. So 1 minus the failure probability equal to, now what at least one principle is correct. Either I have to find out the weakest and most vulnerable one, which is very difficult to find from this, because I mean, I have to use the in the large size limit the percolation statistics, so that's very difficult for small p or so. For very small p, this argument would actually work. I mean, you can find out later. Very small p, that means very small amount of disorder, you can essentially utilize this kind of Lipschitz argument, but you are going closer to percolation but not quite at percolation, because then of course the stress release regions cannot be considered to be independent. So if it is independent, then what I can do is, suppose they are designated by some index I, so product because I am assuming they are independent, that each one survived under that stress. So that is for sure, because I cannot say which one, but each one must survive under this stress. That for sure, and that's the extreme statistics said in the other ways. And then you can write it as e to the power minus, which in some sense is identical to the volume times G sigma. Now remember, I considered GR here in percolation. That is actually that two bonds at a distance or two defects at a distance are member of the same cluster. So that was percolation statistics was doing. I do not have the, I cannot have the benefit of that directly, but here I need the densities of cracks or probability of getting the number of cracks which have strength which starts propagating under stress sigma or less than sigma. So if I know that, then I could find out. Now if I can find it out, that would be a function of sigma only, and that I have to find. But what is f then? F is 1 minus this quantity. Okay, so f sigma is then 1 minus e to the power minus v g sigma, and that already says that g sigma might give you this thing, this form, but what is for sure is if v increases, it becomes even more vulnerable. Exponential, here of course you get f sigma moving with volume this way. Then you have to find g sigma. Now this is difficult, but you have one thing, forget about, since I assume that each of them are independent, for single defect of length L, sigma c was related as 1 upon square root of L. So I have a mapping that sigma c, the breaking threshold of a crack of length L, goes as 1 upon square root of L. There are some quantities which are, and percolation theory gives me that unless we are at PC, this is the form, that to get a defect of size L is e to the power minus L by xi. So G L is going as e to the power minus L by xi. So I can always put L as 1 upon sigma square. So this is GL is GL in terms of sigma. That means, okay, the sigma is e to the power minus 1 upon, sorry, minus e to the power minus 1 upon sigma square into xi. Okay? And if you put that here, f sigma will be 1 minus e to the power minus v to the power minus 1 upon sigma square xi. And this is the Gumbel form. Okay? This is the Gumbel form. I hope I did correctly. Oh, no. This is the Gumbel form, and it clearly has, if you put f sigma, here if you put f sigma, as some finite value, say 0.8 or something, or 0.9, that is failure probability 90%, because to get f sigma exactly 1, you may have to go to real large sigma, but put some finite value, 90% chance that it will fail, will give you a finite value of, for any v, a sigma c, which will decrease with volume in a way that is given by this form, but this form is one of the important form for all engineering mechanics things. The other possibility is that this is the same, but GL goes as L to the power minus zeta. This is at the critical point, and then G sigma goes as sigma to the power plus 2 zeta, and that means F sigma, this is the Gumbel, and Y wool is, this will give you Y wool, and that is F sigma is 1 minus e to the power minus V V sigma to the power 2 zeta minus V sigma to the power 2 zeta. Yeah, this is the Y-wool form. And since engineering mechanics has a very good fit either to this or to that, you can get now using some of this scenario, and you are still assuming that they are not overlapping. And you can see that basically log V is very important to, I mean, for example, here you can easily see that, sorry, here, I mean, in the Gumbel form, log V is very common because V and sigma are exponentially related, so sigma goes as log V for failure. I mean, 1 upon log V. And because if you want to have F sigma some finite value, say 0.9, then you forget about these things, then exponential is also this. So this must be finite number given by this 0.9, 1 minus 0.9 and so on. And so this must be finite. So sigma will be related to V as a log V, 1 upon log V, and that is what simple Lipschitz argument would say. And typically this is for small disorder, but you can see that, I mean, for large disorder, but not quite very large, because you cannot go very close to PC, although percolation statistics that we wrote over there is valid for large P very close to PC, but there it's not a fault there, the fault will be here where we assume that they are all independent, because once you have a very large number of defects, there will be the stress release regions will start overlapping, and you can't do that. So now I want to do the other thing. Now this this part was actually by P. Ray and 1983 onwards, and then 1983 or 85? 85, no? So this derivation was given in 1985, and now I will go to another thing which again Purushottam and me gave, but that is near, but this is in the region where you do not have these regions overlapping. Yeah, sorry.
What is Z in this case? It's there is correlation.
D.
Z. Exponential minus F over Z.
Oh, no, sorry, not D. This is exponential V e to the power, because you said that GL goes as e to the power minus L by xi.
I'm asking about xi only, like you said that there was no overlap.
There is no overlap, yeah.
But still
Stress release regions, yeah.
But still there is a correlation among,
Yeah, that is perfectly all right. I mean, this thing, okay, let me try to, since she asked this question, let me try to do this, this form in one dimension. Okay, you will see that I will not assume any correlation in the form of overlapping. Now, suppose in one dimension you are thinking of bonds or sides, okay? So, Let me see. I don't know whether. Okay, so what is the probability that I consider a bond here or site here and a site here at a distance r? This is the GR. At a distance r, they are member of the same connected cluster. So this one is occupied and this one is occupied. Now in one dimension it is absolutely trivial. GR must be equal to, exactly equal to p to the power r. It cannot be, if any of them is missing, you do not have the connection beyond r. You cannot have up to r. So all these r bonds must be there. So, okay. Now that can be written as okay, let me see, in a different case one can do something like that. Okay, yeah, I think you can write this as e to the power minus r by r into log of 1 by p. So it is here minus, so this is this. E to the power log of 1 upon p to the power r minus that is actually p to the power r. Now that can be written as so that is actually this form, but then xi is something like, or no, I think is in this case it is exact 1 upon log of 1 by p, which can be written as 1 upon minus of 1 upon log p, which is 1 upon minus log of, since PC has to be 1, I mean this PC means that there is a connection from one to another end, so PC must be 1 in one dimension. All bonds must be present. So that is 1 minus PC minus P, but this is exact. I am not doing any approximation anywhere. And then, and for any r, I mean I do not have to consider any, because it is this bond and this bond, they are at a distance, but for that all the bonds must be there, and that means it is, and if this is small, so this is 1 upon, okay, this is not writing, it is actually, it is 1 upon p minus, okay, it is p minus pc to the power minus 1, or yeah, rather pc minus p. So nu p is just 1. Now the thing is, you are trying to find out GR, and in this case, the case that we were considering in the Lipschitz argument, in this case we are exactly doing this way, and I am getting PC as PC minus P to the power nu P is minus 1, and the correlation length is given exactly by 1 minus PC minus P. So now, so this is what we are using. We are saying at a, I mean if you have a defect of, but what it means, GR means that up to R there are defects. So that means the defect size is of the size of R. So if I know that defect size is of the order of R, means here I put it as L, and if L this is, then of course I know xi, then it is in this form, e to the power, exactly it is e to the power minus L by xi, okay, in one dimension. I am not doing it in one dimension, it is exactly e to the power minus L by xi, and xi is 1 upon PC minus P. No, I mean, this can be at any distance. Then, here I did approximations, but here you are doing it. And then, one approximation, you are using the picture from Griffith's estimate. That because I need G sigma, I got only GL, and that too exactly using percolation kind of thing, which is exact in one dimension. Otherwise you cannot do exact things. But once this part is known, in one dimension it is exact, but in other cases you get very accurate things, and with Renotion group support for very accurate calculations, or there are many other ways of computer simulation and so on. And this is a kind of phenomenological thing or an approximate thing, but there it connects, Griffith's law connects sigma with L. So now I can get G sigma. I had GL, I know how to connect L with sigma, so I can get G sigma, and G sigma is nothing but this form. In one dimension you know, in otherwise you know that this has some universal exponent involved in it. So if you do that, you will get the Gumbel form. And Gumbel form will immediately give you this relation, log v, 1 upon log v, square root of 1 upon log v. And this you could argue in much simpler way here, but in one dimensional form. But now here you can do it in a much better thing. Okay? And now I will erase this part, because I need that part still, or maybe I erase this part. Oh no, but you remember this thing. Now suppose, okay, that is the other thing. In percolation, there was a great picture. You are approaching very close to percolation threshold. Now, of course, fractal is an idea, but you are a little above the real fractal limit, P slightly above percolation threshold, but very close to it. So you still have a kind of super lattice structure. That was by a great idea, a picture proposed by, everything is incorporated. Okay, so typically of the size of xi, within the size xi, you have some self-similarity. This is a measure of how much, because beyond that, the system is still compact. I mean, at the critical point, the entire lattice is self-similar. At the critical point. But if you are not at the critical point, the self-similarity starts growing as the correlation length starts growing. You are approaching PC, the xi is increasing, self-similarity region is also increasing. Finally, at PC, everything is self-similar. But you are not at PC. Then what would happen is that you started with a disorder, and then what will happen is that you still see the lattice, but they gave a picture which is at one point it was very, but it's a very nice intuitive thing, and it helps a lot if you can utilize it. And the idea was, as these things are all defined now, okay. Okay, this I erase rather. So the idea was that after some time this lattice will look like this. It is called, okay, Skalskolowski degeneracy, because Sokolowski, huh? Super lattice structure. What is this? This lattice would look like this. And you go a little, okay, I have to And then there are some regions which are multiply connected. Now you have to be imaginative about this thing. What they are trying to tell is that from any end to another end, and this length, this crow flying length from one node to, now previously the node distance was a lattice constant, but near PC, but not exactly on PC. It is still a super lattice. Only thing is, the lattice has a lattice constant which is xi times A or xi. But the links are not just one bond and not xi bonds, they may be more than that. And the length may be, this is called a link. And link is dominantly singly connected. That there are marginal connections, because otherwise some places are there which is multiply connected. So this is only thing. I mean, so in a sense you have, now what you need the superlattice length, which must be the correlation length, and you need the link length, so xi, which is defined, and link length, call it L link. Now that may be xi to the power something, I mean that is p minus p to the power this, sometimes it is said, okay, let me write it as xi to the power zeta, and now this zeta is not what I did for this is a different one. If I have used, okay, let me put it eta. Keep in mind, these links may be, I mean certainly is longer than, I mean this link length, if you stretch it, it will be longer than xi, because xi is from this point to this point crow flying distance. But those who are moving along the link, they will have to go a longer distance, and not always singly connected, sometimes they are multiply connected. Okay, if you are thinking of conductivity, you have to think that these are there and there would be a sharing, and any failure or fuse here would be dangerous, but any failure here would not be dangerous. Okay? So if you have that, how long do I have, Purushottam? 5 minutes?
5 minutes.
Oh, still this cannot be finished, okay? Okay, let me do it, and it's also simple, so I think, but it's simple algebra, but so I have defined the superlattice. The lattice constant is xi, and something is, and xi is, okay. So lattice constant is xi, and which goes as Pc minus P, or P minus Pc here, okay, to the power minus nu P I wrote or something, okay, nu. And this nu P is written here nu because did I use any other notation? Here it is nu, okay. Oh, nu P, okay, let me write nu P. But I am not using any other nu, so let me erase this thing and call it nu, because otherwise many times I have to write. And the other thing is link length is, say, xi to the power eta I wrote, and that means but then sometimes eta is, okay, there is an overestimate if you think that the fractal dimension is essentially coming from this length has this much mass, because within this length you have this much mass, L is the real mass, so xi to the power dB, the backbone dimension, is your eta. So eta is sometimes called the D backbone dimension. It's a fractal dimension because you have the real mass given by the link length. isn't it? And the number of bonds that is there within xi is this. So that means if you have length, as I said, if you have within this length 2L, you have only 3 unit of mass. So that way, if you have within xi distance, if you have this much of mass, then xi to the power dB is this link length. So link length is xi to the power dB. So this is a bigger estimate, because or rather it will give a lower estimate, because you are thinking the entire mass but is equally being used. But there, as I said, these links, these singly connected ones are much more difficult to use, and then this one are much more dangerous. Just a minute. Hello. Yeah, yeah. I am busy. Thank you. And so, and the other thing is, you can take. I mean, actually, eta is less than, maybe equal to this, and it would be greater than equal to, if you consider this is Cornelio conjecture long time back and turned out to be numerically correct, that it goes as I to the power minus, I mean p minus pc to the power minus 1. That means it is 1 upon new percolation. So these are the two things that is there. With this, let us proceed. First is number of parallel links between, I mean, if the stress has to be supported between these, then number of parallel links I mean, as xi increases, it will decrease. So xi to the power, okay, one dimension is there, and there, I mean, in 2 dimension you will have in 2 dimension is xi to the power minus 1. And is that clear? Because you will get more and more, I mean, now parallel links, the number of parallel links will decrease as xi increases. Okay, eventually there would be one link only at the critical point, but otherwise this. Then stress per link say sigma link is sigma, and number of parallel links will share. You will have to divide the total support is, I mean, total this many number of links are supporting this stress sigma. So divided by this number. So xi to the power then sample strain is sigma by y, of course, that you said that it is a linear system and something like this. So that would be, that strain would be shared, I mean that strain would be shared by this link and this link. So that also you have to find again. So strain, sample strain per link is this much by number of links. So that means it is okay. So first one estimate. One estimate is, as I said, for linear systems there are other ways of estimating. Sigma is sigma, but people know that y goes as this modulus of elasticity has been studied, that it is p minus pc to the power say t elastic. I don't want to, I mean this can be found out with some other connected to this correlation length exponent and other things. I am not going into that. As I said, this elastic or any linear response is perfectly defined quantity as p goes to pc and volume goes to infinity. People have tried to find out conductivity in a random resistor network. I tried to show how it grows near PC, and that exponent is some linear exponent which is known from percolation statistics. So let us, if that is, then it is sigma xi to the power, let us write everything in terms of xi. Xi is p minus p to the minus nu, so Te by nu. No, sorry, this one is this sigma, and then it goes as xi to the power p minus pc to the power Te means xi to the power 1 minus 1 upon T nu, and into minus 1 upon to the power 1 upon nu into T or TL, Te, but y was below, so it is minus is gone, plus Te by nu. Sample strain is this, okay, T by this, and then strain per link, that let me call that, this will be required, epsilon L, because stress per link, strain per link, and that would be needed because I have a limiting value of the elastic energy for each link or each link bond, and then according to that I will try to find out the same kind of thing Griffith did for the original lattice, which was intact. We have to do it now using the super lattice picture near the percolation point. So that would be, per link means this thing divided by the number of links, so that is plus minus d minus 1, so that is sigma no, this was sorry, and number of links is this one, xi to the power minus of d minus 1. So this is the total stress divided by how many links? These many links. So that is xi to the power this Te by nu minus d plus 1. Strain energy per link element is then
maybe in
I'm okay, so okay, maybe okay, maybe I will have to continue later on. So okay, let me tell you the what I am after. So Griffith did it that, I mean, you trying to find out the energy which will be given to the surfaces. So you try to find out the elastic energy must be sufficient to produce the surface energies. Here I will try to find out what is the elastic energy that is stored here. Now to find the elastic energy, now the problem is I do not have the elastic medium. Now the elastic medium is now of different structure. It has the link length is no longer the link, no distance between the links is no longer the kind of mass of the link. So if this increases, the stress per link increases, and that is shared, I mean the elastic energy is also shared by the number is given by the inverse of this correlation length sorry, but link length is this, so I have to divide the elastic energy by the links, so I have to get the elastic energy per link. For that I have tried to find out stress per link, strain per link. I will have to go to the elastic energy per link, fix it, give it to a maximum value, then find out the breaking stress. So that that would be the Griffith's analog, and you will see that in a sense you could perhaps guess, just 1 minute, we found out sigma c is surface energy density modulus of elasticity by length. Now this length will be replaced by xi. I mean, you will find that it in a sense does that. This will be given by xi to the power, because it has a p minus pc to the power this thing, so this will be given by xi to the power T elastic by nu, and this is nu is the correlation length. This will be given by xi to the power dB, because the surface energy will scale with the backbone dimension. Essentially this will be given, and you have to see when this will be valid and when the other picture that we will maybe I will not have the time in the next one, because I have to come to the fiber bundle model in the next lecture. So anyway, that's my thing. In a sense, this calculation will tell you that Griffith calculation, in a sense, with the surface energy density going as xi to the power backbone dimension, modulus of elasticity going as p minus pc to the power Te, and that means xi to the power this, and maybe this is minus, maybe this is minus, and then this length goes as correlation length. You just put that, you will get it from more rigorously from there, and you will also know when this will be valid and when this will not be valid. That I will do very briefly in the next talk, and before going to the final one, fiber bundle model. Sorry, thank you, I had to rush, and